Good afternoon, everyone. I'm just looking on the login script here, and it looks like some people are still signing on. So we're going to give it a couple more minutes to allow them to have a chance to log on. But the webinar will begin in a few moments here. So thanks for your patience. Okay, everybody, we're going to get started. My name is TJ Willits with Veolia Water Technologies, and I'll be your moderator for today's event on optimizing Kraft pulping and recovery cycle operations. And that's the name of our technical presentation for today. Water circuits at pulp and paper mills are becoming tighter and more restrictive, and to maintain them operating with maximum stability and productivity, the concentrations of non-process elements that accumulate within the facility must be managed. So that's what we're here to talk about today. Before we enter into our presentation, I just have some housekeeping notes here. Obviously, you should be hearing me speak now. There's two options for audio that you could select. You could either listen to the webinar via your computer, or you could call in using the call-in number there. So if you're having issues with your audio, feel free to switch and try the other option. On the right hand of your side too, there is a questions panel. Feel free to enter questions throughout the presentation. We have some time near the end of the presentation to have our technologists review and answer those questions. After the survey, you'll be directed, after the presentation, will be directed to take a short survey. Please take a few moments, it should take only about 3 minutes, just to give us some feedback about today's presentation. And also at that survey, you're able to enter in some information of topics related to water, wastewater, crystallization, or evaporation that would be willing to maybe cover for the future. So your feedback does matter, and just take a few moments to fill out that survey. Just want to spend a few moments talking a little bit about Veolia as a corporate entity. Veolia designs and implements solutions with our three key pillars in mind: water, waste, and energy. And it's our goal to make sure that we maximize these resources as much as possible for municipal industrial clients. When looking specifically to pulp and paper, we look to help pulp and paper companies with their water, evaporation, and wastewater challenges. And you can see on the right hand of the screen our suite of capabilities and what they cover. Everything from black liquor concentration, precipitator ash treatment, influent or wild water treatment, utility water, wastewater, and water footprint reduction, as well as mobile water services as well. Veolia has been involved in supporting leading pulp and paper companies around the world. Our resume includes partnerships with these companies for a variety of different applications. And globally, you could see that our reach as a corporation is quite far. We've expanded almost on every continent for providing pulp and paper technologies and projects as well. We do this with more than 350 technologies that we use to integrate, and you can see some of those technologies that are listed there. And today we're going to talk about CRP as one of the ones, as well as some other evaporation technologies as well. So we're going to enter into our technology presentation, optimizing Kraft pulping and recovery cycle operations. We have with us today Michael Begley. He's the Senior Process Design Engineer for Veolia Water Technologies. He has over 30 plus years of experience and has a special focus of working with pulp and paper companies as well. He's actually working and just in between a project right now in South America, so we really value his time and sharing his knowledge with us. So at this time, I'd like to turn the webinar over to Michael. Michael, are you with us today?
Yes, I am. Okay, we have some main areas that we work in the pulp and paper out of the Chicago office here, Chicago and Bilbao office with the HPD technologies. Mainly we do black liquor concentration and evaporation and all the associated stuff such as soap skimming, foul condensate stripping, methanol recovery, etc., and NCG collection in the black liquor concentrators. And we also specialize on treatment of the precipitator ash to remove chloride and potassium, and as a byproduct be able to produce SOP or potassium sulfate. Our HPD office, we're evaporation and crystallization experts. We've been doing evaporation and crystallization across many industries, over 85 years of experience. We're the world's largest evaporator and crystallizer company. Many installations, many different sizes, in many different industries, and we're ISO certified. And a little bit of the technologies of how Veolia fits into the pulp mill. Veolia has some areas that HPD, we're not going to cover here because they're not my expertise, but we treat the influent water, boiler feed water, cooling water, and all the wastewater and effluent treatment for the mill. The HPD technologies focus on the black liquor concentration and the chloride removal, chloride and potassium removal from the recovered boiler ash. For black liquor concentration, there's a lot of words here, but really what it is in the pulp mill, they're going to cook the wood chips with chemicals. They're going to get a soup that's going to have the fiber that they're going to recover, and the chemicals are going to be in the liquid phase. So we're going to get the liquid phase that they wash off the pulp. It's going to come to the evaporators, usually at about 12 to 15% solids, and we concentrate it up to recover the water and to recover the chemicals. So you get condensates with the water, which have to be tailored to mill usage, and then you concentrate the liquor typically up to 70 to 85% solids, where it can be burnt in the recovery boiler. The organics are burnt off to generate power to run the mill and generate electricity, and the chemicals then go to the lime kiln and they're recovered back in the process. So it's one of the bigger steam users in the mill, so we need to be very efficient in how we integrate it. There's a couple different technologies we use for black liquor concentration. We have an enhanced force circulation, and we use switching falling film. Normally the enhanced force circulation we use in North America, partially because it's catered more to smaller mills and a few other things. Some of it's very stable without washing. It's very resistant to insoluble scales. A lot of the mills in North America, you tend to get a lot of calcium scales, which would tend to follow switching falling film. And it's very mechanically sound, but it doesn't scale up well for large mills. But mills in North America like it. You'll see at many places a 30, 60-day boil-out cycle on the system with that. The switching falling film is a different approach. You take a falling film evaporator, and you assume that it's going to scale, and you just have multiple bodies. You'll have 3 or 4 or 5 bodies. One of them is on wash, the rest are operating, and you cycle through, and every 4 hours or so you go to a wash. This has a lot of switching valves. The solids do cycle a little bit every time you switch, and it does have a weakness of insoluble scale. But for a lot of these mills around the world where you have a scale that washes easily, it works very well, such as for eucalyptus liquors. And it also scales up very well, so all of the large systems in the world have that because it's not practical to do an enhanced force circulation for some of these giant mills that are being built around the world. The forced circulation, you can go either with a horizontal or vertical heater. The main difference is the horizontal heater takes a little bit more footprint, but it has a little less power requirement. Other than that, functionally, they're pretty much the same. Next, the big difference with our forced circulation units is we have enhancers that we put inside the tubes. The point of them is we want to mix the liquor to get a higher heat transfer coefficient and to reduce our power requirements. So we have these enhancers that we put in. They're along the surface of the tube, so they peel the liquor off the outside of the tube, mix it with the bulk liquor. It also has a big opening in the middle so you can hydroblast it in case you make a mistake and plug the thing up. It usually has a 1-inch opening, and compared to normal or open tube technology, it reduces the power by about half, and you get about double the heat transfer coefficient. So it makes the power comparison very competitive with a falling film type unit. A couple of units. The first place we put it in was in Longview, Washington in 1995, the 77% solids. And then we've got a series here of a few other places we put it. 98, we put it in Bennettsville, South Carolina to replace some falling film units, going up to 80%, works very well there. Valiant, Oklahoma has several different units there we've put in over the years, up to 75%, an 80% unit added in 2006. And Port Wentworth, we added on to a plate type unit. We did a capacity increase by converting a 6-effect train to a 7-effect train. So we got better steam economy, went to higher solids, got a capacity increase, and got much more stable operation with the forced circ unit. And at New Bern, we did the same thing. We had some falling films that we replaced to get a better operation, higher solids, and more stable operation, better economy. Those are usually the things you'll see in common with most of these upgrades. And also in Selma, Alabama, we integrated one to go up to 75% with a 6-effect LTV evaporators. And then we get into some of the new falling film trains we do around the world. One of the more recent ones we've done is a 7-effect evaporator system for the Klabin Puma mill in Telemaco, Borba, Brazil. It started up in 2017. It's a 7-effect falling film going to 80% solids, 1,700 tons per hour with an integrated ash treatment, integrated stripper, soap skimmer, methanol integration. It's a very large state-of-the-art system, and they're doing an upgrade there, and we're building a new train to support the upgrade, another 7-effect train to support the upgrade there. And one of the recent North America trains we did was Weyerhaeuser Grand Prairie, where we put in a new 7-effect evaporator to go to 80%, again, to replace some old LTVs, so much better steam usage, higher concentration, and that started up some years ago. And those were also large vessels that we built up and transported to the site in one piece. And some more photos of Grand Prairie showing the construction, built a building around the bottom of the units and left the top exposed. And some photos of them being barged up to the job site. And H-Pulp in China on Hainan Island was a 1,450 ton an hour evaporator set that we built, going to 80% solids. That was an equipment only project. So it had very high steam economy, low pressure steam design so they can generate a lot of electricity. And again, we had very high quality condensate and methanol stripping and rectification there. That system's been in unit for several years. And then back on this side of the world in South America, we have CMPC in Santa Fe, Chile, a system we supplied some years ago, but it's 1,050 tons an hour, going to 78%. It's been since increased to about 1,250 tons an hour. It was a turnkey system with very high steam economy, low pressure steam again, so they can generate a lot of electricity. It has a special condensate system so that we can take all of our condensate out as a condensate, all around 100 ppm of methanol, which is a very good condensate for recycling throughout the mill. And we can also control the amount of A and B condensate we take out of the system. We've been doing that for years. It's been very successful and saves them having to dump any condensate to the effluent treatment, which can be very sensitive to the odors in the area. This system also has a CRP system and a stripper methanol system. And then a couple other we have in South America. We have Veracruz E-Line, which makes 80% solids, has the same condensate system that we had at Santa Fe, where you can control the amounts of A and B condensate you make. And then Veracel we had done before that, new mill in northern Brazil. We had a 6-effect system there. And then Veracruz, you'll see several of them here. We go backwards to the D line, which makes 80% solids. Again, it was one of the, I think it was the first system in the world to use 7-effect economy and low pressure steam. And it made 3 condensate fractions, which we had some control of, and methanol stripping and rectification there. And some more photos of the D line at the giant Veracruz mill. And then one of the more, a North America mill is Smurfit Stone in Hopewell, Virginia, a 6-effect system with a concentrator and a foul condensate stripper, and ash treatment system there also. Okay, another thing I want to talk about is our chloride removal process. It's a process that we have for treating the precipitator ash to remove the chloride and potassium out of the mill. Works as a kidney for the mill to remove these non-process elements. And we'll talk a little bit about process, principles, and then ECRP, and again, the potassium production, or potassium sulfate production. Typically, or historically, the ashes from the recovery boiler have been reintroduced to the black liquor to recover the chemicals. This recovers the sodium sulfate and sodium carbonate. What we found is if you get the chloride and potassium in the mill, there's been a lot of research. The recovery boiler tends to concentrate those, so you get a very high concentration of them. So if you treat the ash, it's a very effective way to remove the chloride and potassium because they've been pre-concentrated by a factor of somewhere between 2 and 4 in the recovery boiler. This technology was introduced to the pulp and paper industry in the mid-90s. Many references from 1 ton an hour to 22 tons an hour, and there's actually some that are larger than that now. It's typical crystallizer technology. We have many crystallizers in many things, production for sodium chloride, sodium sulfate, sodium carbonate. So we use a lot of those principles in designing our ash treatment system. And what you do is you dissolve the ash, you recrystallize it. What you're going to do is the first things you crystallize out are the sodium carbonate and sodium sulfate, and then the impurities are left in the purge in the liquid form, and you purge those out. And a couple examples, we had one in Eastover in 1996, steam driven and condensing in water. New Bern has one in 2009, a little bit bigger, integrated with the evaporator train. We did one at Vizzy in Australia. What was interesting about that one is we did that as a module. We actually built the entire system in New Zealand at a shop, put it on a boat and put it on a truck, brought it to the job site and dropped it in. And I think they were running within a week after the system showed up on the job site. They just made the connections and started turning the thing on. So it was a very successful system from that standpoint. And then one of the newer, larger systems at Suzano Mucuri in Brazil is 550 tons a day. This system replaced 2 leaching systems. By doing that, we were able to remove their salt recovery by about 100 tons a day, which is a lot of salt to take out of the effluent treatment, and it's a lot less chemicals that they make up. Those chemicals that they make up, it saves them a lot of sodium sulfate makeup, but it also, by recovering the sodium carbonate, it saves them a lot of caustic makeup in the mill. So it's been a very successful project. And much better boiler operation also, because we're getting better removal of chlorides and potassium, because they were, in both cases, they're treating all of the precipitator ash that's available. Okay, this I talked about a little bit, but really what we do in the process is we dissolve the ash in condensate, use crystallization to make pure crystals. We keep the impurities stay dissolved, which you purge out of the system, and you return the salt cake or the purified salts back into the black liquor. We have very high chloride removal, usually between 95 and 99%. It's easy to operate. It scales up to larger systems. It's actually more difficult to operate a 2-ton-an-hour system than it is to operate a 20-ton-an-hour system. These bigger systems run very well. And you get very high sodium recovery with these because we get the good washing on it. And the one limitation with this is normally if you have high potassium, that hits us first, and we end up having to purge on potassium. Okay. And typical flow scheme, which shows that you dissolve the ash in water, you pump it into the crystallizer, a typical crystallizer, 4-circulation crystallizer. We do the evaporation. We have an elutriation leg that gives a first stage of washing before we go to the centrifuge, so we get very high, very clean crystals out of it. We can keep a very high concentration factor between the feed and the purge, which is what makes it very efficient. And we use a pusher centrifuge so we can wash the large crystals. And this is very typical. It's used in many industries to purify various salts. And there's a couple ways to integrate it. One of the things is, how do you integrate the heat with the mill? The easiest way, if you're putting in new evaporators, is you just integrate it with the evaporators. Normally you drive the system with first effect vapors, put vapors back into the number 4 shell. That's the easiest and most effective way. If you do have demon water that's going cold in the aerator, or you're heating it with live steam, it's even more efficient to just put in the system, drive it with live steam, and heat demon water. That's very stable. And if we can't find any other operation, you can put in an MVR where you drive it with electricity. Typically, steam is very cheap in a pulp mill, and electricity is a little more expensive, so that's normally not the first choice. And this is what a pusher centrifuge looks like that we use. Again, the pusher means the cake gets pushed along the bowl of the centrifuge and pushed out. There may be more than one stage in there, and you wash the crystals. You first draw the water out, then you wash them and push wash water through. So you get a very clean crystal out of it and a very dry crystal. You'll see what the crystals look like there. I mean, that's coming off the centrifuge. There's very little moisture, usually about 5% moisture. And that's how we get the better efficiency. Because we have very little moisture, the impurities are included in the liquid. So if there's no liquid, there's no impurities. The crystals themselves are very pure. And then to manage the high potassium, we invented this enhanced chloride removal process to deal with mills with very high potassium, which is the case for most of the new mills in the world. especially mills processing eucalyptus because they typically have more potassium. If we look at the phase diagram here, we can see that the glasurite solubility is a function of temperature. We take advantage of that in ECRP, and what we do is we take a second stage and we cool the purge, and we cool the purge, we crystallize glasurite out of it, which is a potassium salt and a potassium sulfate. So it allows us to concentrate the potassium in our purge. So we make this glasurite, which is it's 3 potassium sulfates and 1 sodium sulfate. It allows us to, if we just do that on its own, we get about 22% potassium in the purge as a limit, as opposed to about 11 to 15%, which means that you cut your purge rate in half if you're limited on potassium. And you just need a little bit of steam, and allows you to independently control your removal of potassium and chloride, because the potassium now comes out as a solid and the chloride comes out as a purge. The other added benefit of this is you preferentially take sulfate out as a glasurite crystal, meaning you're going to remove more carbonate. Most mills have their sulfur balance is such that they have extra sulfur, they can't recover all of their sesquisulfate. So this allows them to recover more sesquisulfate and buy less sodium hydroxide as makeup chemicals, and has a very favorable cost impact on the mill's makeup chemicals. This glasurite is mostly potassium sulfate. So what we can do is we can take this for a larger mill. It doesn't make sense for most of the smaller 1,000-ton-a-day mills, but when you get up into these larger mills around the world, you get enough glasurite that you can convert it into a fertilizer. What you do is you partially melt the sodium sulfate out of it, leave the glasurite crystals or the potassium sulfate back. You collect those potassium sulfate crystals, and then you can dry them and save them and use them and put them back in the forest as a fertilizer. It's a very valuable fertilizer, and it's actually getting removed from the forest by the trees, so we're able to reintroduce it back into the forest. So it's a very green technology. And this is a program, this is kind of what I just described, where we take the purge, go to a second stage, cool it, centrifusion, add water, and recrystallize it in the SOP that we take off as a product. And typically, this is an example from one mill where you move on the phase diagram on the trend curve, that as you get, below 5% chloride, you're really just improving your corrosion. When you get below 5%, then you start to see a big difference in the sticky temperature, and you start to see improved boiler performance, and you can run your boiler hotter to make hotter steam and generate more electricity. And typically, for what this ECRP or SOP system will do in a large mill, normally you can cut your purge rate by about 50%. It's more efficient if you have higher potassium. We cut it by more. If you have higher chloride, then it's going to not be as strong. On some of these large mills, you'll be about 50 tons a day of caustic makeup. You'll reduce compared to a conventional CRP with an ECRP. Some may be up to 100 tons a day. So it's a very big economics for this. And then the other thing is you're preferentially recovering carbonate and sodium carbonate over sodium sulfate, which helps the mill's sulfur balance. And the amount of SOP you can produce is going to be somewhere between 600 and 1,500 for these new state-of-the-art mills, which is a lot of fertilizer. That ends up being, millions of dollars a year worth of fertilizer. And some photos of the glasurite we produced under a microscope, and then the next photo is some SOP that we produced. So you get fairly clean crystals. And the last thing is this digitalization, Aquavista. We have a system where we can remotely monitor the plants. do a lot of automatic reporting and things like that. It's a new system that we've been marketing lately. If you want to add anything on that. Okay. Yeah.
Okay, that concludes the technical portion of our presentation. Just want to remind everyone that on the right-hand side of the screen is the question panel that you could go ahead and ask a question, and we'll try to get to as many questions as possible. Just to kick things off, we do have a first question here, and it would be, what would be the first step in engaging to review and analyze to see if one of these technologies makes sense to incorporate? Michael, are you still there?
Yes, I'm sorry.
You must have been on mute there. So just to repeat the question, would be, what would be the first step in reviewing to see if it would work to incorporate one of these technologies in a pulp and paper facility?
The first step is probably to get some data on what size the system is, what condition it's in, what the future conditions, so we can go through just a preliminary economic analysis to see if the investment makes sense, whether it's an evaporator, if you want to add a new concentrator. Normally you can save some operating costs because you're going to have steam savings, and then not doing boil outs is going to save you a little bit of money, and you're going to save some maintenance costs. And you have to put together a package like that typically to justify any of these type of packages. And then also for an ash treatment system, it's the same thing. You have to look and see. For a very small mill, many times you can just purge a little bit of ash and it's going to make up for it. We have to justify our system by being able to recover chemicals, that you have to recover enough chemicals to pay for a new system. But we can work through those numbers. We can get target chemistry where the ash is with them and try to figure out if it actually makes sense or if it's just too small. Whereas when you get to these new large mills, there's no question you need these technologies.
Okay, another question we have here is, when considering ECRP or CRP, what would be the main drivers in considering between those two technologies?
Normally the main driver, the reason for developing the ECRP technology is for mills that have a high potassium content in the ash. That the CRP process gets limited. You have to take a very large purge based on the potassium to purge the potassium. So this ECRP allows us to make a difference. So on some mills, you have maybe a difference of 1 or 2% in sodium recovery. On other mills, we might be at 95% with an ECRP, where we're limited to 70 or 80% with a conventional unit. And between that and the size of the system will let us know whether or not it makes sense.
Okay. Well, that's all the questions that we had put in on the panel. However, Michael's contact information is listed there on the screen. So if you have any additional questions about some of the things that he presented today, please don't hesitate to reach out to him directly using that email. Again, just some other reminders. Please take the survey after the webinar. It'll help us improve these presentations, and also feel free to enter in some topics related to the water, wastewater, or evaporation, crystallization that you would want us to consider for future content for us to present in a webinar. Again, my name is TJ Willits. I'm the moderator for today's event from Veolia. Thank you to Michael Begley from Veolia's HPD group. And at this time, this concludes our presentation. Thanks and have a great day.